And one thing about the railway tracks that I think is important as well, that I'm just drawing a sphere here very quickly. So I know you all know what a sphere looks like, but a visual aid does help. You can see that at the North Pole, these two lines converge, and at the so-called South Pole, they also converge, right?
Yep.
In spherical geometry, these two lines are supposed to be parallel to each other, and they converge, right? That's in the definition of the spherical geometry.
Yep.
Now, if I'm on a railway track and I look forward, then I will see the railway tracks converge to a point. And this is the important part. If I now turn 180 degrees and look the other way down the railway track, they're also going to converge to a point.
Yeah, they don't go spread out the other way.
They don't spread out, right? So basically what I'm saying is that that's also a very clear indication that it's spherical geometry we're working with, because only spherical geometry can do that. Converge in front of you and converge behind of you, like the North Pole and the South Pole do. So your vision, that's another example of, I'm not saying it's a proof, it's an observational experience that shows you that these axioms of visual geometry are spherical and that they are self-evident and that you can observe and experience them yourself.
Well, it's an evidence, I reckon it is a proof. It's an evidence that your vision is spherical.
For me, it is too.
Because you do know those lines are parallel.
Yes, I could walk down that railway track and I know they're not getting smaller. And the further I go, they're still going to converge. Yep. So it's, in that respect, it's just like spherical geometry is, yeah?
When the geometrician draws a diagram with the most perfect accuracy, when he keeps his eye fixed upon it while he goes through a long process of reasoning, and demonstrates the relations of the several parts of his figure, he does not consider that the visible figure presented to his eye is only the representative of a tangible figure upon which his attention is fixed. He does not consider that these two figures have really different properties, and that what he demonstrates to be true of the one is not true of the other.
And, I think the person who discovered it was a guy called Thomas Reid, who you probably heard me talking about. He was a polymath in Scotland, who was the first person to write about the geometry of visibles. And the first, or probably one of the first to make the distinction between tangible geometry and visible geometry. And he wrote not quite extensively, he did some experiments, which I think are great, and wrote about it, and basically defined 10 or 12 axioms without going through any of the further mathematics. And it's exactly the same axioms that Riemann used 70 years later to define his, or what Gauss and Riemann both used to define the curvature of the Earth. I think about 70 years before Riemann, so about 1750, was the first guy to really, dive into it in any detail. And I'm pretty sure that he got sidelined and sidetracked, and the people saw what he'd done and reused his mathematics to make the deception work properly.
So they were both very courageous, and they were both very insightful. They were geniuses. Okay, they really deserve a lot of credit because they went out of their way. They saw a new world, and they were not afraid of venturing out there and figuring out what's going on. But the story is really a sad one, okay, because even though they did this remarkable work, they were ignored by their contemporaries. Okay, so now I want to tell you, well, what is this geometry actually? Right. And here's, I guess, where I have quite a different point of view on things. But I think that This is a sad chapter in many ways, but one of the reasons it's sad is because people really there was this very easy opportunity to discover non-Euclidean geometry years and years before, and it somehow had been ignored. People got sidetracked by Euclid's 5 postulates. Instead of just asking, what's the natural thing to do? What should we really be doing here? It's hard for us to imagine how important Euclid was to these people. It was like a Bible. It really was like a religious text. So if Euclid said there were 5 postulates, then there were 5 postulates. It wasn't a matter of opinion. They really took it completely literally. And unfortunately, they took it too literally instead of thinking, well, what's really going on here? If they had asked what's really going on here, they would have realized that there was a non-Euclidean geometry right in front of their nose, and it had been for millennia. Okay. There is another non-Euclidean geometry. In fact, arguably, it's the most important geometry historically. What's that? That's the geometry of a sphere. The geometry of the surface of a sphere. That is also a non-Euclidean geometry. It shares many similarities with Euclidean geometry. You can still talk about points. You can still talk about lines. You can still talk about triangles. You can even talk about distances and angles if you want. You can talk about areas. You can talk about proportions. This is in the proportion 1 to 2. And in fact, this kind of geometry had been studied for millennia. Ptolemy had studied this. All the astronomers were more interested in spherical geometry than they were in planar geometry because, as I've mentioned many times, the night sky is obviously a sphere. What goes on in the night sky is really happening in the celestial sphere, and so it's obvious that the sphere was important.
Any normal man can agree that visually the 2 rails of the railroad track truly appear to meet in 2 places, though they also truly appear to be completely straight. That there is the geometry of the pure visual field is a double elliptic geometry seems so obvious once one grasps it, that one feels that this must have been recognized, even taken for granted, by previous thinkers who have spent much time on the relationship between geometry and vision. Reid was the first, and I believe the only, philosopher of standing to hold the thesis set forth in this paper. Only recently has Reid's position begun to attract the attention it deserves. If our thesis is correct, a great many intelligent men have been systematically mistaken for many centuries.
So let me be very clear, and I'm going to tell you what these problematic topics are. Okay. The first one is the foundations of Euclidean geometry. That is a problematic logical topic. To start Euclidean geometry properly is highly, highly difficult. And I've talked already in this series about that, about the difficulties of the foundations of Euclidean geometry. And they are there for sure. Sort of at the higher levels, there's often a lot of really solid, and one can be pretty confident of what's going on there. But the difficulties are often at the more foundational issues, at the bottom, where when it's actually sort of setting up the foundations of the subject, there things are not so clear-cut. There's more interpretation and ambiguity possible. So it's really maybe even at the high school or even primary school level sometimes, or maybe first year or second year undergraduate level, at those areas where we're introducing fundamental definitions and so on, that problems can certainly arise, and I think they certainly have. I think modern mathematics has severe foundational challenges, and that probably we're seeing a time where there very well may be quite a lot of reversals in how we think about foundational things. So suppose that we were on a large infinite plane. There was no trees or houses or anything. We were just on a flat infinite plane, and the only thing that was on this plane was an x and a y axis, and maybe these coordinate lines equally spaced. And suppose we could press a button, and then suddenly this graph would be illuminated. So suddenly we'd press a button, and there in front of us we would see y equals x squared. Okay, this is a thought experiment. Okay, we're on this infinite plane. There's nothing else around us except for us, and we just press this button, and now y equals x squared appears. What would it look like? If we actually stepped back and looked at it, what would we see? We wouldn't see this. We would see something else. And this is the kind of picture that the Renaissance artists were interested in. And here's what we would see. There would be the horizon. And here would be the x-axis. And here would be the y-axis. And here would be x equals 1, and x equals minus 1, and x equals 2, and minus 2. And then there would be these lines that would all go towards this point at infinity, because they're all parallel. So like railway tracks, they would all converge here. And the line where y equals 1, the line where y equals 2, the line where y equals 3, these would become closer and closer spaced. Exactly the same way as I drew that tiled floor earlier. Now what would happen if we press the y equals x squared button? Well, 0, 0 is on it, 1, 1 is on it, 2, 4 is on it, 1, minus 1 is on it, 2, 4 is on it, 3, 9, where would 3, 9 be? 3, and then 9 would be up here somewhere. Minus 3, 9. About 4, 16. 4, 16. Minus 4, 16. The whole thing would be illuminated and would look like this. That's actually what you would see. If you had a camera, you had your mobile phone, and you just press the button, and there was the parabola, and you looked at it, the horizon sort of level with your eyes. You looked at it, you take a picture, and then you come back and show your friends. This is what they would see. The parabola would actually appear as an ellipse.
Well, for me, it was about understanding the roots of mathematical physics, right? And understanding these differences, the separations in the sciences, and looking much closer at how mathematics has been turned into this godlike, I don't know, godlike theory, godlike concept, godlike proof and evidence, and so for me it was very much that. Also looking at Thomas Reid and the visible geometry and understanding how those manipulations have been used in the global deception to equate visible phenomena with real physical substances. And that's only done by mathematical trickery, if you ask me, nothing else, right? And I can see that better than others, maybe. So it certainly helped me come to the point saying, wait a minute, that's all nonsense what I've learned. If I look at the real world facts, practical, demonstrable stuff, then that does not apply. Why it's correct to use the circular arc, because our eye is globular, and the back of the retina is a curved surface, so that what's happening at the back of my eye in my retina can be represented by an arc in front of my eye, which is why I've set up these geometric diagrams that way. And then there's basically, you know, the planar angle that you need, and there's basically only two theorems that you need to know to understand direct vision. And direct vision, the theory of direct vision, I think, is different from the theory of perspective. Perspective for me is representing 3D objects on a 2D planar surface by mathematical rules, whereas the theory of direct vision is applied to how your eye works. It's, you know, geometrical optics rather than paintings or drawings, yeah, or technical drawings. And there's only two theorems that you really need to know, and that is that objects have that proportion respectively as the angles under which they are seen. And I've got geometrical proofs in here, right? So I went through all the diagrams, did all the proofs, and also show in here, you know, certain things that people take for granted, but they shouldn't take for granted. So things, it's not as simple as saying, if something's twice as far away, then it's going to be half the size. You know, that's what ballers tell us, right?
Yeah.
But it's actually a lot more complicated than that, depending on the situation of your eye and how the object is. But just to go through the argumentation, so when you look at the horizontal spacing between two things, then if I go from H to A, then the horizontal spacing is moving from U to T. And when I go from here, from A to C, it's going from T to S. And when I go from C to F, it's then going from S to R. Those are the 4 points that I have there. And this angle here between S and R, if you can imagine that this angle here, the difference between these 2 points is going to be, when I go further away, so small as to be insensible. And that's when the limits of vision are reached. And when that happens, and it's probably due to the fact that we only have a certain amount of rods and cones on the back of our retina, that we can make that differentiation. But basically that angle is so small that we cannot longer differentiate between these 2 points, you know, from our eye limitation. And that's when this whole horizontal space disappears from view. And anything sitting in that horizontal space also disappears from view, because you can't tell one point from another. And if you go even further to the right, then the same principle kicks in with angular diffraction, the Rayleigh criteria, which basically says that 2 light points can't be distinguished from each other. So you have the vision limits of the eye, and at some point you have the visual limits of nature. And when that happens, those points are no longer distinguishable. Anything in this interval is then lost to sight because it's no longer distinguishable. You cannot see it anymore. And you can see from the top half that the angle's still a lot bigger, right? So this angle has not reached that limit the same way the bottom part has reached the limit. The bottom is always going to reach that limit sooner because you're closer to the ground, or closer to the bottom of the object in this case.
That's why the sun looks like it sets.
Yep. The tangible object is very much Euclidean planar geometry. That's what the whole world is constructed on, levels and perpendiculars and parallels. But visible object is not. It actually obeys the rules of spherical geometry. Now, you might, or we'll all find that in the first instance a little bit tricky to understand, because you'll say, but I don't see things curved, Gavin, right? And the explanation of that is that if you're at the center of that sphere looking out, then of course you will not see the outward curves of the sphere. So when you're looking at something, you'll see it as a straight line. But that doesn't mean that the geometry of visual perception is not spherical. Just because it looks Euclidean, it's not. It's actually spherical, right? And because we direct our attention to things, we're always looking straight on at stuff, and it appears to be Euclidean because you will never see the outward curve of your own eye, right? You will always see the same way that if I, you know, put something like this, it looks like a line, right? And you don't see that it's a plane, right? It's a similar problem, yeah? So we don't attend to visible figure, and we don't realize that it's spherical in nature and not planar the way they tell it is, because they confuse the definitions of perspective, and you know they have us looking at flat screens all our life, you know, and so we tend to think everything's just planar.
This is how they've tricked people, surveyors, into believing that they're actually measuring a ball.
And I think you've been attacking it from that same angle as well, Chris, right? You know,
Yeah.
and we all know that in all these different things in astronomy and geodetic surveying, where we know they're lying to us because water can't bend, it's that simple, then there has to be a simple way that they've tricked everybody, because we're not all stupid, right? And it has to have something to do with, or at least from my point, it has to be something to do with we don't quite understand how the eye works and how our mind does not attend to the things properly, and some mathematical sophistry and manipulation of things like spherical geometry and 2 spheres and 3 balls is the way that they've done it. I mean, these are, for me, the kind of major components of the deception. Yeah.
Exactly.
Yeah, that's how they fooled the academics like you know? That's how they were able to pull it off.
Yeah.
Absolutely.
The common people, it wasn't as hard. They didn't have to. But for people who actually went into the field of study, they had to have a way to actually trick them as well.
One of the interesting aspects that Gab's come up with too is the explanation of how it was actually done, how Gauss and Riemann basically reinstituted Reid's thinking, but changed it to use it in this deception. And it looks like it was deliberate too, doesn't it?
Yeah, I'd say it was deliberate. For me, the mathematics works the same. If you're on a round ball and you tell everybody that they have planar vision, i.e. what they would normally call perspective representation, then the geometry of everything that you see and all the appearances is the same as if you were on a flat plane, but you had globular vision, spherical vision. So spherical vision on a flat plane is the same as planar vision on a spherical surface. So it's just switched round, if you like, yeah? One of the arguments that they always have is that they say that Polaris, you know, a sighting of Polaris, whatever degrees Polaris is sighted at, is proof that we're on a sphere, because on a flat plane it apparently wouldn't work. So the globe argument is that the light rays come from Polaris. We are all on a globe, and if anybody takes a sighting, then it will correspond exactly to your latitude on a sphere. Yeah, you've heard that argument, right?
Yeah. Oh yeah.
And the proof that it doesn't work on a flat plane is this one, where they say it would only work at 2 specific points, namely if you're directly below Polaris or you're at 45 degrees. Everything else wouldn't work. It would all be wrong. Yeah. So, but if you look at it basically from another point of view, namely this one. So this is the whole thing that I modeled then in GeoGebra, which is basically, again, showing their argument first. So this one's kind of showing, there's my latitude at 45 degrees. I'm on that circle of latitude and I'm observing Polaris, then it would be a 45-degree angle. That would be correct for basically any latitude. I've given 2 examples here of 52 and 18. But the other way to look at it is that if I do an orthographic projection of that latitude down onto a flat planar equatorial circle here, then that's that blue line here in the middle. If Polaris, the more if 0 is the North Pole, if we take, if you like, similar to the azimuthal, so that latitude is actually the distance from the center, and longitude remains the direction around the circle, then it actually works out to be exactly the same. That the further I go from the center point, we know that Polaris drops visibly in the sky, yeah? So that if you basically think of latitude and longitude as being the distance outward from a North Pole center rather than circles on a sphere, then it's absolutely perfect